Failure analysis plays a critical role in material testing by pinpointing the reason and the method behind material failure, aiding in the comprehension of failure models and root causes for the engineer and research. This knowledge allows for the advancement of design and enhancement of material selection and improvement in quality control, thereby avoiding potential failure in future. By taking action on this problem beforehand, failure analysis guarantees the safety, effectivity, and durability of engineering systems, cut expenses, and promote innovation. Furthermore, it helps with regularly compliance by ensuring products adhere to strict safety and performance regulations. In general, failure analysis is crucially for the progress, technology, and preservation of systems integrity.
Next, I would like to talk about common failure models. We have three common, which is corrosion failure, wear failure, and factoring failure. Firstly is about corrosion failure. Corrosion failure happens when the chemical reaction with happen with the environment and often landing in material failure. The location of corrosion is on a pipe and cursive that can be lead to a material failure. Next is about wear failure. The progressive removal of material due to relative movement between a surface of contact with a substance. Lastly is about factoring failure. The suddenly or gradual failure of a material due of a cycling of or constant stress often cause above improvement material selection and design flaw. Next.
Now we see testing techniques. Various methods of material testing to failure analysis include tensile testing, impact testing, hardness testing, microscopy, and non-destructive testing (NDT). Every method assists in recognizing failure modes in distinct manners. First, we see about tensile testing. Evaluate how a material reacts to the stress applied in one direction. Procedure: a sample is extracted until it fractures dominating stress strain patterns. After that, we go for impact testing. Evaluate how well the substance can soak up energy while breaking. Next, hardness testing. Evaluate the ability to withstand indentation. A tough indenter is pressed onto the substance with a set of force. After that, microscopy. Investigate characteristics of material at the microscopic level. Electron microscope for enlarging and examining the surface and internal structure of the material. The last one is NDT, also can call non-destructive testing. Assess the characteristic of substance without causing any harm. Consists of ultrasonic testing, radiography, and magnetic particle testing, and dye penetrance testing.
I represented a case study. Topic of our case study is the elimination of composite drive shaft in a racing car. The problem of the case study is composite drive shaft in a racing car experience premature elimination. It's leading to a potential safety hazard. Taken in our failure analysis is OM and SAM. For optical microscopy, we polish cross-section of the delaminated area were prepared and examined under a optical microscope. This helps identify the nature of the delamination, the presence of voids or imperfections, fraction and the fibermetric interface quality. While for scanning electron microscopy, high resolution SEM image provided detailed information about the fracture surface morphology, revealing features like fiber pull-out, fiber breakage, or evidence of matrix cracking.
Next, I would like to talk about a root cause investigation. Firstly is NDT. NDT is a stand not destructive testing. Not destructive testing, we can use a tree, which is ultrasonic testing, extra or CT. CT is a stand for computer tomography, and lastly is a thermography. Ultrasonic testing used to detect and map the extent of deflimitation with a component layer. Second is X-ray. X-ray technical can provide the detailed internal view highlighting delimitation and other defects. Lastly is about thermography. Thermography can define area of deflation by detecting variation in a thermal conductivity. Second is mechanical testing. Mechanical testing, we use ILSS, stand for interlinear severe strength and fluxural and tensile testing. LISS test is a measure the shear strength between a layer to determine if the deflation is due to weak interlaminar bonding. And lastly is about flexural and tensile strength. Mechanical property of the composite material can compare them with the design and specific. Next is
Assalamualaikum, my name is Surya Natasha Industry, and number is J22A0161. Okay, next we go to preventive measure. Material selection. Microscopy driver material selection. Leverage OM and SEM findings to refine material selection. OM if denomination shows uniform fiber distribution or porosity. Select a material with better fiber alignment and avoid control. SEM if weak fiber to resin bonding or evidence of matrix cracking is observed. Choose a material with improved edges properties or a different resin system altogether. Next, design modification. Microscopy inform design optimization. Use OM and SEM result to refine the drive shaft design for better stress distribution. OM if delamination occurs at specific location. The design can be modified to reduce stress concentration in those areas. SEM if microscopy cracks are found near stress concentration concentrator, the design can be altered to create smoother transitions or incorporate reinforcement. Next, we go to process improvement. Microscopy for quality control achievement. Integrate OM and SEM into the manufacturing quality control process. OM regularly perform inspections to ensure proper fiber alignment and void-free composite structure. SEM conduct random sampling to verify optimal fiber resin bonding and detect potential matrix weakness before large-scale production. Next, we go to quality control microscopy aided preventive. Next, we go to quality control microscopy aided preventive maintenance. Utilize OM and SEM for proactive inspections during preventive maintenance. OM school periodic visual inspections with OM to identify early signs of delamination or surface crack. Next, we go to SEM. Conduct NDT inspections with SEM at regular interval to detect internal like microscopic crack or weak bonding before they become. Next, we go to collaboration with industry. The racing team can provide details about the car's design, usage, patterns, and any unusual event that might have stressed the drive shaft. The material supplier can share insight into the material's properties and no failure modes. The university lab can analyze the microscopy data and correlate the observation with the information from the racing team and material supplier. By combining knowledge, data, and the details information option through OM and SEM analysis, a more comprehensive understanding of the delamination cause can be achieved. Next, we go to possible causes of delamination identified through microscopy. Improper coring OM might reveal uneven resin distribution or voids, while SEM could show weak bonding between fiber and resin, suggesting incomplete coring. Next, if fiber break, SEM analysis of the fracture surface can reveal characteristic of fiber break, indicating fatigue and overloading. Metric cracking. SEM imaging. The SEM image might show crack with the asymmetric, potentially due to high stress or incompatible material selection. Depending on the causes, corrective action can be taken, such as selecting a composite with a better resin during process, implementing stricter quality control measures during manufacturing to ensure proper fiber element and void elimination, modify the drive shaft design to reduce stress concentration, establishing preventive maintenance school that include endoscopic inspections for early detection of delamination or fatigue damage.
Conclusion is we can prevent similar failure in the future and develop new material with enhanced properties. Next, we become better problem solvers in a broader perspective on material and solution. Lastly, it drives innovation by exploring the potential of new material and technique. Thank you.